Hi, my name is Scott Simpson, and today I'll be talking about the ideal gas law, or as most people know it as Hidner. So where you have P, V equals nRT. And that's oftentimes how most people describe it. So what is this used for? Well, it's used for calculating different physical aspects of a gas. So in some cases we could calculate pressure, some cases we could calculate the volume at which that gas would occupy, assuming ideal gas conditions, the number of moles of this system, and the temperature of this system. R is a constant. So let's go through and pick apart each one of these variables. So I already previously alluded to that P is equal to pressure. V is equal to the volume the gas occupies. N is the number of moles of gas. T is the temperature. And R is an ideal gas constant, which I will give the value for in a little bit. Now, the units to which you need all of your variables in depend on what value you choose as your constant. So in most cases, this is expressed in liters times atmospheres per mole degrees K. Or well, just K. So if you're using this constant with these units, you have to make sure your pressure, your volume, the number of moles you have, and the temperature are all in the same units, so they end up canceling out. So in this case, if you were using this gas constant, pressure would have to be in atmosphere, ATM. Volume would have to be in liters, or L. Moles of gas would have to be moles. And the temperature would have to be in K. Now, how do we get all our values to this point, or into these units? So a lot of times you'll be given units of pressure, volume, temperature, and moles that aren't quite in the units that you want them to be. So you have to convert to get to those points. So an example of this is for temperature. It's often reported in degrees Celsius. So let's say we're looking at 25 degrees C. How do we get that to K? Well, the temperature in Kelvin is equal to the temperature in degrees C plus 273.15. So all we have to do to figure out what 25 degrees C would be in K is take 25, add 273.15, and we end up with 298.15 K. Now, there are various ideal gas relations that are talked about in general chemistry, such as Boyle's law, Charles' law, and Avogadro's law. But in reality, you do not need to memorize those to use that information. So let's go through an example. Our first example will just be looking at Charles' law. So we're going to justify how we can use our standard equation of state, or the ideal gas law, PV equals nRT, instead of having to remember all these little laws like Charles' law. So let's mark this curly. Charles' law. And this one has to relate changing volumes and changing temperatures with one another. It's equal to V2 over T2. And this is assuming pressure and the number of moles are constant. So let's figure out how we can use PV equals nRT instead of this law here. So we're going to try and get to this law from basically PV equals nRT. All right. So we have P1, V1 is equal to N1. R is just a constant. It's always a constant. It's equal to T1. And we also have P2, V2 is equal to N1, or N2, excuse me, T2. Now we need to have these relations, we need them to be equivalent to one another so we can set them equal to each other and then solve for the variables that we need. So we need volume over temperature. Now, these two equations can be manipulated around so that on one side we have P1, V1 over N1, R, T1 is equal to 1. And then we can also do the same thing for this bottom equation. V2 over N2, R, T2 is also equal to 1. Since they're both equivalent to 1, we can set them equal to one another. So, P1, V1 over N1, R, T1 is equal to P2, V2 over N2, R, T2. Now we have to remember what we said was constant in the beginning. We said pressure was constant, right? And we said that moles are constant. So knowing that when we go from state 1 to state 2, our pressure is going to remain constant and the number of moles is going to remain constant. So P1 will be equal to P2, which we're just going to set equal to P. And the same thing goes for N1 is equal to N2 is equal to N. Now we can sub that back into this equation. What I'm going to do is erase some of this so we have more space. So we're going to sub this in to that equation over here. So now we have P V1 is equal to N R over T1. P times V2 is equal to N R T2. Now if you notice, we have a bunch of constants that we can group out front. So let's do that. We have P over N R times V1 over T1 is equal to P divided by NR V2 T2. And if you notice, we can pull this coefficient out in front of our variables and we can cancel this. So that ends up canceling out. And we end up at our final result, which happens to be Charles' law. So this just goes to show you that you can use the ideal gas equation to get to Charles' law, Boyle's law, or any law that you essentially need to involving the ideal gas equation. So that's fine and dandy, but we should move on to a real-world example where we have some real-world data. So let's say we wanted to measure an amount of helium. And we can measure our atmospheric pressure or the pressure of the gas inside a vessel. So our example question will be, what volume does 6.00 grams of helium at 726 torr occupy? Assuming T is equal to 25 degrees C. So we know we have to use the ideal gas equation, so let's write that down. PV equals nRT. Now, what are we looking for? We are looking for what volume. So we're looking for volume. We're given moles in a way, or the amount of helium we have. We're given the pressure, and we're given the temperature. So the only variable we do not know is that of V. So all we have to do is solve for V in this equation. So V is equal to nRT divided by P. So let's go through and list each one of our values. R is just the ideal gas constant, which has been given to us, so 0.08206 liters times atmospheres mole K. We also have temperature, and that's given to us in degrees C. If we notice and we look at our ideal gas constant, we don't have C, we have K, so we have to convert our temperature to Kelvin. So we add 273.15, which ends up leading us to 298.15 K. Next, we have pressure. And in this case, it's given in torr. Let's check our ideal gas constant. Do we see torr anywhere in here? No. But we have atmospheres, which is a unit of pressure. So let's convert to atmospheres. You just have to know that 760 torr is equal to 1 atmosphere. So let's do our conversion. 760 torr is equal to 1 atmosphere. Multiply that through. We end up at 0.955 atm. So now we have our pressure. Now we need to get to our moles. So in this case, we have grams. Grams is not in our ideal gas constant, so we have to figure out how many moles we have, because that is in our ideal gas constant. So we know we have 6.00 grams of helium. We look at the periodic table, we can see that there are about 4 grams for every 1 mole of helium. When we multiply this out, we'll divide this out, we end up with about 1.5 moles of helium. So now we have all of our variables, or our values, that we need to plug into this equation. So now let's just plug and chug. So let's do that. So, let's write our original equation of state down. B is equal to N RT divided by P. We have all of our values. Be sure to write in your units to double check to make sure you have your units in correctly. And we can check to make sure our units cancel. Typically, in general chemistry, if your units cancel, you're going to get the right answer. So double check and be sure your units cancel. I know it's a pain, some people hate to write out all the units, but it really helps you out in the long run. K divided by 0.955 atm. So let's look at our units right now. So let's start with moles. We have moles here, and then we're dividing by moles in our constant, so moles are gone. We have degrees K here. We're dividing by degrees K. That's gone. We have atmospheres in the numerator. We also have it in the denominator, so now that's going to cancel out. And we're left over with liters. And that makes sense because we're solving for volume, and that's what we want our units in, is in liters. So now solving for this, you should end up with about 38.4 liters of gas, or the vessel should be that size. So hopefully I've demonstrated to you the importance of the ideal gas equation, how you can use this equation of state to figure out other laws such as Charles' law, Boyle's law, and you can look at changes in different systems. So going from system 1, P1, V1, N1, T1, to system 2, P2, V2, N2, T2. And also how to use real-world data to solve for different variables that you would like to know, assuming ideal gas conditions. So with that, I'd like to thank you. If you have any comments or questions, feel free to email me, or please leave a comment below.